Welcome back, guys. I'm in a little bit of a challenge with Zoom of all things. Anyway, it's working now. That's why I got a little bit of a start late. Okay. What I plan to do is obviously finish the chapter that we're started on, and then I'll do some examples from the worksheet, maybe one or two. I won't start another chapter. Don't forget, uh, Tuesday will be a study day. I will be here. So come Tuesday, next Tuesday, if you have any questions, feel free to drop by. If you don't, work on that exam and be good to go. Okay. All right. So where were we? We were on slide 8, which is that one, but I'm gonna go back and refresh your memory just so you won't forget about all of these types of reactions in stoichiometry. Okay. The main thing to take away from here is I cannot go from point A to point B, apples to oranges. I keep using that. I know I sound redundant, but I keep emphasizing that to help you out. Is I cannot do that unless I go through moles. Moles is the common factor that can allow us to go directly from point A to point B. Also, we can't go directly from grams of given what we're given in the problem to grams of what we're looking for, grams find. We can't do that directly unless we first convert everybody, specifically grams given into moles, okay, based on the molar mass. And then based on the chemical reaction, we have the mole ratio that then relates the mole relationship between what is given and what we're looking for, what we're trying to find. That's what the mole ratio's function is. And that puts us into units of moles of what we're looking for. Hence, we have moles of fine. From that point, once we got moles, depending on the problem, we can figure out the volume if we are at STP, and that's where we go to the bottom right corner, or given the formula of what we are looking for, calculate molar mass and then convert that to grams. Okay. When we first started the examples, we were in the inside, in the box, white boxes. We had moles given. We were looking for moles defined. Now we expanded it to include grams now, because as I stated in the lab, we're not measuring in moles, we are measuring things out in grams. Okay. So in this question here, they ask you to write and balance the reaction of hydrochloric acid, aqueous, with solid HCl. Okay. Solid HCl. So the first thing I need to do is to write the equation. So let us begin with that. Now, a couple of bits of information that you see that is given to you is the fact that it's telling you the oxidation state of cobalt. Let me change the color here real quick. It's telling you that the cobalt, okay, will be a +2 ion when the reaction proceeds. Okay, so we start hydrochloric acid, HCl, and we need to know that information about cobalt because why? Because cobalt's a metal, obviously, right? But it's one with a variable oxidation state. It's not part of the 16. Recall I talked about giving you the 16 elements, the metals that we knew 100% of the time, their oxidation state. So in this case, cobalt is not one of them. So we need to know that amount of information because the oxidation state can vary. Therefore, also furthermore, because it's a variable oxidation state, we use Roman numerals to tell us what is the oxidation state if we need to write that name out. Okay. All right. So we have HCl, aqueous. Okay. In the presence of hydrochloric acid, excuse me, hydrochloric acid in the presence of cobalt. which we know is a solid, okay? And the reaction proceeds. They're telling us that because this cobalt is telling us cobalt +2. But the question is, how do I know what this is? Does, can you look at that equation, HCl plus CO, cobalt? And is it reminiscent of any of the types of reactions that you've been doing before that we've done already? There's only 6 types of reactions. Obviously, this is not a combustion reaction, right? It's not an acid-base reaction. We got no hydroxide, all right? It is, what else do we have? Okay. See, I'm going through the process of elimination to determine what type of reaction do I have here. It's not a combination reaction. Normally, a combination reaction consists of 2 elements coming together to give us a compound. The hydrochloric acid is a compound. Okay, so that's not a combination reaction, nor is it a decomposition reaction, because normally a decomposition reaction, we have a compound that is broken down to their elements. And so we eliminated 4, right? Combination reaction, decomposition reaction, combustion reaction obviously is not here. And what was the other one? Acid-base reaction. Yes, we have an acid, but we have nothing here that produces hydroxide, a hydroxide. So therefore, we're left with what? A double replacement reaction and a single replacement reaction. Well, look at the single replacement reaction, the general type. Normally, we start off with two aqueous compounds. We don't have that scenario here. We have one, HCl, but cobalt's a solid. So obviously, the only thing left is the single replacement reaction. Okay, and that's what I did. I'm offering you here a suggestion on how to determine what type of reaction I'm looking at by remembering the 6 types and then eliminating the ones it's not. Eventually, I will get to the type of reaction that I'm dealing with here. And once I know that, that helps me now to figure out what's going on. Because if we recall from a single replacement reaction, one metal replaces the other. One metal is in hydrochloric acid, one metal is in an ionic material, is in an ionic state as a compound, and the other one is an element, right? And the metals interchange. But then you might ask, oh, wait a minute, but hydrochloric acid, there's no metal in there. And you are correct. But if you think about the single replacement reactions, the next thing you think about, hopefully, is the activity series. And if you look at the activity series, I mentioned this, that you see the metals all, this metal is greater and more reactive than this metal, but they were all relative to what? Hydrogen. That's the H in parentheses, okay? And so that scale is based on hydrogen, either in the form of H plus or in elemental form, hydrogen gas, okay? And so if anything's going to replace anything, what's going to happen is the hydrogen will be replaced by cobalt if the reaction proceeds, and it will, because you're told that up here up front. They're telling you that, but we're verifying that it is. And so this is H plus, which is the salt form of the hydrogen gas. Remember, we compare which one is more reactive. And what we find out here that cobalt is more reactive than hydrogen. Okay. And then the next question is, well, okay, is cobalt in salt form? No, it's not. It's in elemental form. Therefore, we have reaction. Okay. Which tells me that the cobalt will become ionic and the hydrogen proton will go back to element. And so the products we're going to get will be the hydrogen gas, because again, we're displacing the hydrogen, which is, remember, H plus in this form. Well, it's going to go back to the element to form H plus, H2. And cobalt is going to combine, replace the hydrogen. But before we put them together, let's put them in ionic form first. And we're told this from the problem up in the top. It says cobalt will be in the +2 state. What do we know about the chlorides? Well, hopefully by now you realize that chlorides are -1. So in group 7 will gain 1 electron, chlorine will, and therefore becomes chloride. So its oxidation state will be -1. We need 2 of them to counter the +2 of the cobalt. Therefore, the formula will be cobalt Cl2. And furthermore, we go to the solubility rules, and you'll see that the chlorides are soluble. It's in the it will be number 4 in the solubility rule table, where the halogens. This chloride is soluble, so therefore we can put HQ. Okay, so we have the reaction here. Now you see how we went through this to determine. Now the next thing before we go any further is we balance. So we got 2 chlorides here. Let me put these together so we all. Here I am putting carbon monoxide down here. Okay, solid and aqueous. Okay, those are the states. So that's our reaction. Now we get a balance. We got 2 chlorides on the right side. So if we put a 2 in front of HCl, that balances the chlorides, CLs, and that ups the hydrogen. Well, that's okay because H2 is diatomic, and therefore we're good in the hydrogen. Okay, so we got 2 hydrogens, 2 chlorides, 2 chlorides, 1 cobalt, 1 cobalt. We're good to go. Okay, we're eliminating here. We're done with that. Don't want to erase all that and to confuse you. So here's our balanced chemical equation. So let me redo this here so you can see how we went in to attack this problem. We're given a reaction. Okay, we're asked, it's in words. We need to convert it into a chemical reaction. It tells us hydrochloric acid and solid cobalt react, balance the reaction. Well, we need to figure out what type of reaction it is so we know what kind of product it is, right? We went through the process of elimination to determine what type of reaction of the 6 it is not. Okay, so we went through that process of elimination if you didn't recognize what you're working with to begin with. So we eliminated all of them, right? And we ended up with the only logical type of reaction left would be the single replacement reaction. But it was confusing because you saw HCl. Normally, single replacement reactions are dealing with 2 metals. To refresh your memory, the activity series, the reactivity of metals is relative to hydrogen gas, and that's why hydrogen is involved here. H plus is the salt form of a hydrogen. Okay. So we went through the series to determine who's more reactive, cobalt or hydrogen. Cobalt's more reactive. Is cobalt in the salt form? No. Therefore, reaction occurs. We simply replace the cobalt with the hydrogen. So that means the hydrogen, which starts off in the +1 charge as a proton, goes back to elemental form, which is H2 gas. Okay. We're given the oxidation state of the cobalt, which is a +2. We know the chlorides, they're going along for the ride. They start off as a reactant. They're going to end up in the product state, part 2. We know they have a -1, so we have to write the ionic compounds first as ions so we can put them together in the proper ratio. We write the formula. We came up with COCl2. It's soluble based on the solubility rules. Okay. Therefore, it's aqueous, and we have the chemical reaction written out. We finalize this by balancing it out, and we played with the elements, numbers, till we can get it and to get it balanced. So we ended up with a balanced chemical reaction. Okay, let me take my junk out and we'll put in the good stuff here so you can see it. All right, so we have two hydrochloric acids react with one cobalt to give you cobalt 2 chloride, okay, plus H2 gas, a single replacement reaction. Okay, so now you're going to be asked questions since it's a typical type of questions that one may be asked. Question is, how many liters of gas at STP will form if you begin, if 5 grams of cobalt reacts? Okay. So let's first isolate what we're given because who are the main parts of this reaction? Well, we look at the reaction. We're asking for how many liters of gas? Well, obviously the only gas formed here is hydrogen, okay? Good thing to know is STP. Why? Because we know at STP, we can use this relationship. We know that the volume of 1 mole of gas would be 22.4 liters per mole. So that's a conversion factor that we can use, okay? Will form if you have 5 grams of cobalt reacted. So 5 grams of cobalt reacted, our only concern is between cobalt and hydrogen, and that's it. Don't care about any of the other guys. They are there in the proper quantity to have this reaction proceed. Okay. All right. So we determine who are the key parties in this calculation. Okay. We look at them, everything's balanced. So we see it's a mole ratio of 1 to 1. So that really makes it pretty easy. That tells you that whatever number of moles of cobalt I have, I'm going to have essentially the same number of moles of hydrogen because it's a 1 to 1 relationship. All right. So, but then they're asking, we don't want moles. We want to know volume. Well, that's no problem. Right. What have I always stated when you have a question, you're given, write down what you're given. You're given 5.00 grams of cobalt. Okay. All right. We are looking for, that's given. What are we going to find? What we're looking for? We want to know how many liters of gas are involved. Okay. Guess what? What does that tell me? That tells me that I know that the last conversion factor, because I'm at STP, will be the 22.4 liters per mole, right? Because that's what I'm looking for, liters, and that factor would give me that. All right, so I'm in grams, and like I stated, before I can do anything, I need to convert that grams to moles. So cobalt, what's that number? 58. According to the periodic table, it's 58.93 grams per mole. That is the atomic weight of cobalt. And I simply got that from the periodic table. I put it with grams in the denominator because as I do the math, grams cancel, leaving me with moles of cobalt. It gives me moles in cobalt. Now, that's how much material started off with in grams. I converted that to moles. Now I need a factor to get me to moles of hydrogen. And that comes from the balanced chemical equation, which tells me that there are its stoichiometric relationship is 1 hydrogen to 1 cobalt. Okay. Straight from the balanced chemical equation. So cobalt cancels out, okay, leaving me with moles. These are units of moles, moles of hydrogen, moles of cobalt, leaving me with moles of hydrogen. Now, since I'm at STP, okay, I can use this relationship, and now that would get me into liters of hydrogen gas. Beckmann units cancel out, moles of hydrogen cancel out, leaving me with liters of hydrogen, okay? And so now I set the problem up, just following my units, putting the values in there, and I'm good to go. I verify that my units are set up properly, and I just need to go. Now, what happens occasionally, and I want you to keep an eye out, is this. You look at the first conversion factor. That is the atomic weight. What I find is that occasionally students put the atomic weight on the numerator, and they end up with this. Now, think very carefully when you do that, okay? Because this says 58.93 moles per gram. So think about it, okay? A mole is 6.02 times 10 to the 23rd. It's just not right, okay? The units of atomic weight are grams, whatever number it is, per 1 mole. That you just have to put in long-term memory. And so this setup right here is totally incorrect. Okay, putting the atomic weight with moles per gram. It's 55, and this is 58 grams per mole. All right, so let me clear up my mess here and bring down the good stuff here. We can read it. Okay, so we write down what we're given. Like I stated, we got 5.09 grams of cobalt. The first factor converts that grams of cobalt to moles of cobalt. Okay. Remember, just to keep track of where you're going. Okay. Our relationship that we're only looking at is between hydrogen and the cobalt. Okay. So to get there, I gotta get whatever I started in grams, whatever units I'm given of what I'm given, I need to put that into moles. And that's what the first conversion factor does by dividing by the atomic weight of cobalt. You get moles of cobalt. The next one as I stated, is the relationship, the stoichiometric relationship from the balanced chemical equation between the two components that you're dealing with, whatever they may be. Here's hydrogen and cobalt. That's why I circle them. That's who I'm dealing with. And I circle them so I can remember that's who I'm dealing with. And I don't care about hydrochloric acid, nor do I care about cobalt 2 chloride. They're not involved in this calculation. So that stoichiometric relationship is a 1-to-1. But keep putting my units in there, okay, keeps me in line with respect to telling me and showing me that I'm going in the right direction. Because again, as I proceed, grams of cobalt cancel there, moles of cobalt cancel there, and I'm now in moles of hydrogen. Okay. Adding my final conversion factor because I'm at STP and I'm looking for liters. Okay. And I forgot here because over here I got, I write it down so I won't lose track of what I'm looking for. Okay. I start off with 5 grams of cobalt and I want to get to liters of HCl, of gas. Okay. So finally, it's a matter of plugging in the numbers, and I end up with typing the numbers out. Also, by keeping track of my units, again, I can't overemphasize that. I know that unit-wise, I'm where I need to be based on the question. Okay. So now it's a matter of you plugging in the numbers, and you should come up with 1.90 liters. Now, keep in mind that that conversion factor, the 22.4, is a not exact number, okay? That's number, that's the symbol for pound number, it's not hashtag, okay? It became hashtag recently, but it's been pound for a long time, okay? So that number is an exact number, 22.4 liters. So that could be a factor with respect to your sig figs, okay? We don't use the atomic weights because they come from whole numbers that are the average of whole numbers, which tells you have an infinite number of sig figs. So we don't use them, but do use the atomic weights from our periodic table. Okay. And obviously the other numbers are exact, 1, 2, exact numbers, but 22.4 liters could be a factor. And if this was given to you in 5 point, let's say 010, we got 4 sig figs, and then our answer would be, let's say, I shouldn't say 0, but let's make that 5.000. Then this would still be the correct number because 22.4 liters is what would govern the sig figs. If this number was 5.0, then we would have to eliminate the 0 there, and that answer would be 1.9. Okay, so keep that in mind. Keep that in mind when you're doing these calculations using the 22.4 liters. Okay. Let me stop for 2 minutes and I'll be right back. Okay. Sorry. Thank you. I need to take care of something. All right. So there's that first example. Now, based on that, you might get a second question. Now you might, for this question, they're asking you, if 2.374 liters of hydrogen gas are formed, then how many grams of HCl reacted at STP? Okay. So I'm not going to do the whole scenario I did earlier. I just continue to use the balanced chemical equation we have. We're going to deal here with HCl and we're dealing with hydrochloric acid. Okay. That's our relationship there. And they're telling you that if I started with 2.374 liters of hydrogen gas, okay, how many grams of hydrochloric acid were needed to generate 2.374 liters of hydrogen gas? Not concerned about the guys in the middle there, okay? Just between hydrogen gas and hydrogen gas and hydrochloric acid. All right, so we write down what we're given first, as always, 2.374 liters of hydrogen gas. We're stated in the question that it's stated that we're at STP, which is good because we can convert that liters of hydrogen gas to moles. If we were not at STP, let me emphasize, if STP was not even stated at all, you cannot go any further, okay? Because You can't use that relationship if you are under any other condition than STP, 0 degrees in 1 atmosphere. So we're telling you here STP, but they may say it as 0 degrees in 1 atmosphere. You need to remember that is STP. If they say 25 degrees in 1 atmosphere, then the only answer you have is I cannot calculate, not enough information. Okay, so the first one converts us to moles of hydrogen gas. And then again, as always, we need a second conversion factor ratio that comes from the reaction, okay? And that is a stoichiometric relationship between hydrochloric acid and hydrogen gas, which is a 2-to-1 mole ratio. Okay, based on the balanced chemical equation. At this point, unit-wise, we are now at moles of hydrochloric acid. We're asked to go to grams. So what do we need? We need the molar mass of hydrochloric acid, and that the chloride is 35.45, hydrogen's 1.01, gives you a total of 36.46 grams of hydrochloric acid per mole of hydrochloric acid. Now, once I got that set up, I want to, as a check my units. Liters cancel there. We're good there. Moles of gas cancel. Moles of HCl cancel. We are grams of hydrochloric acid because we're there, because that's what the question asked us to put us in, grams of hydrochloric acid. Now it's a matter of doing the math, and you end up with 7.72 grams of hydrochloric acid reacted to generate 2.374 liters of hydrogen gas. Okay. All right, let's clear this out. All right. So this example here is a good example of, I think, of everything we've been talking about with respect to the elements and knowing what ions they form, what's their oxidation number, so we can put them together as compounds. Being able to now to take something written and converting that to a chemical equation, as we did here up in the first steps, and then balancing the chemical equation. And once we have that balance, now we can calculate whatever they shoot you. You can either do calculations with respect to the reactants themselves, okay? And that's the thing I want you to kind of, understand that we can calculate, once we have a balanced chemical equation, we can calculate between reactants, okay? But we can also calculate, obviously, between reactants and products. So HCl and hydrogen, or cobalt and cobalt 2 chloride for hydrogen, okay? And we can go in both directions. Right now I'm shooting the arrow in one way, but it's a two directional arrow with respect to the calculations. The thing to remember is, one, you need a balanced chemical equation, okay? And whatever you're given, you need to be in moles. If you're not given your initial quantity, moles, you need to find a factor that puts it into moles. Okay, and normally you end up with 3 conversion factors, as we have written right here. Normally you need one that converts, if you're given something in grams, you need the first conversion factor converts it to moles. The second conversion factor comes from the balanced chemical equation. And then in this case, we were at STP, so we could have used, we can use the 22.4 liters. Or they could have asked how many grams of hydrogen gas is created. Well, that last one would then be replaced with the molar mass of hydrogen gas. Okay. All right. So Here's another one. I won't take too much of your time here. We're getting, but let's break it down here. Here we go again. Where's my arrow? All right. In words, I'm telling you HCl gas plus water, no, excuse me, plus oxygen gas produces chlorine gas and water vapor. Okay. Now, in this example, they're giving you all the reactants, they're giving you all the products. You don't have to depend on figure out what type of reaction you have so you can figure out the products. Okay. Like we did in the first one. Because the one we just did, they didn't give you a lot of information. They just told you write and balance the reaction of two reactants. So at that point, I needed to go through all the reactions to determine which type of reaction I'm dealing with, which then tells me what type of products I have. Okay. Here, they're telling you everything that you need to know. Okay, so let's write it down. We got hydrochloric acid, H. Now here's the crazy thing. When it's a gas, we call hydrogen chloride. Okay. But with this, that was AQ is called hydrochloric acid. Okay. All right. Plus, right here, obviously the term plus tells you a plus sign. Oxygen gas, the keyword gas tells you that we're dealing with the diatomic oxygen. Okay. Produces is the word for the arrow. And here we go again. Chlorine. Notice the term chlorine. I-N-E, not chloride, I-D-E. Gas tells us that we're dealing with diatomic chlorine, which is a gas. Or people will pronounce it chlorine. Tomato. And water vapor. Good old fashioned and tells us it's the plus. And water vapor, hopefully you know this, H2O. It says vapor, which means it's a gas. Okay, so we're on the gas phase here. Okay. Now here's the neat thing to remember about this reaction. So they're telling you how many liters of chlorine gas can be formed if 3 liters of oxygen react completely at T. So we got 3 liters of oxygen. Okay. And they want to know how many liters of chlorine are made. Okay. That's what we're dealing with. Oxygen and chlorine. Don't care about the other guys. Now, the other thing is this. We are at STP. Being at STP tells us, okay, we can use a 22.4 liter per mole relationship. Now, the interesting note here, I want you to remember, guess what? We are in gas phase all the way around. All the reactants are in gas phase, all the products are in gas phase. So that might be good information to know here as we proceed with setting this up. Okay, so my apologies, I forgot to balance it. So this is balanced. Okay, we got a balanced chemical equation after I wrote it down. I forgot this step. My bad. So it takes 4 HCl's, 1 oxygen, and 2 chlorines, CLs. I say CLs because they could be in the form of chloride or chlorine. So I just CLs, 4 of them. Okay. We got 4 as a product, 4 as a reactant. And then we got 2 H2Os. That gives us 4 hydrogens, and 2 oxygens. So everybody's balanced. Okay. Write down what we're given. Question says that we start off with 3.00 liters of H2O. No, liters of O2, excuse me. All right. Well, we're at STP, so we obviously can use that factor there. That puts us into moles of oxygen. Okay. Then we go to the stoichiometric relationship between the chlorine and the oxygen, which is a 2-to-1. Okay. And like we've done before, we're still in H2O, we're still in STP. So now we can still use the 22.4 liter per mole relationship because we're at STP. Doing the math, we end up with 6 liters of chlorine gas. And note something here. Is there anything we can do to simplify this whole calculation? Do you recognize anything there that we can do to simplify this whole setup? Does anybody see anything? And the way the math was set up? Okay, let's double check my units. Make sure everybody cancels out. Let me make sure I'm a different color here. So my liters cancel there, moles cancel there, moles cancel there. I'm back to liters. Okay. All right, where I should be. Okay. But do you see a relationship here? Notice, let me clear this out here. Notice what's something cool about this. First of all, like I said earlier, we're all in the gas phase. We're all in STP. But do not, this factor and this factor, don't they just cancel out automatically? 22.4 divided by 22.4. Don't they just cancel out just by default the way it's set up? Okay. What are we left with? The mole ratio between the two reactants. Okay. And we're not being asked to do any gram calculations or anything like that, because then we're just being asked to go from liters to liters. When you're being asked to go from liters to liters, you're in STP, and everybody is in the gas phase, and especially the ones that you are working with directly. All you simply need is a stoichiometric relationship between the two. Okay, and moles of oxygen will cancel. Moles cancel with each other here, leaving me with units of chlorine, which is what we're looking for. So only in those conditions you can simplify your calculation, but just using the stoichiometric relationship, which is a 2-to-1 mole ratio. That means if I have 3 liters of oxygen, I'm going to have 6 liters of chlorine. Okay. Right. So try these at home. Good time you try these and see if you can work them. It says carbon reacts with oxygen gas to form carbon monoxide. And how many liters of carbon monoxide at STP can be made from? You start off with 15 grams of carbon and 20 liters of oxygen gas. Okay. There's 2 questions here. How many liters? No, there's 1 question. I thought there was 2. No. There's 2 questions. If I have, how many liters of carbon monoxide are at STP can be formed from? First question, 15 grams of carbon. Second question, how many liters of carbon monoxide at STP can be formed from 20 liters of oxygen gas? Okay, different conditions. All right. With that, you should end up with 28.0 liters of carbon monoxide and 40 liters of carbon monoxide for question number 2. Okay. Try those at home. And if you can't figure it out or need a better understanding of it, Tuesday is a perfect time to bring it in and we can go. So let me quickly overview these calculations here. Okay. Well, of what we've been doing. we taken the elements, as I stated before, and from the elements we were able to we know that some we're going to form ions, positive ions and negative ions. Okay. From that, we're able to put them together to make compounds. So they from the elements we make compounds, be it ionic compounds or covalent compounds. Okay. The compounds then react with each other. We have 6 different types of reactions that we have dealt with. And from those reactions, we are able to generate the products, and then we balance these reactions. Okay. From the balanced chemical reactions, we have those coefficients, which are the stoichiometric ratios between reactants and products. How many moles of everything is created or generated in a type of reaction, any reaction. And then we have calculations of reactants or products based on these ratios in terms of moles, grams, or liters if we are at STP. Now, if you're given moles, you don't need the molar mass. You just go for moles in the stoichiometric relationship to moles of what you're looking for. But if you start with grams and you need grams of product, you've got to convert everything to moles. Moles is the common factor for these reactions. And if you are dealing with liters or want to determine liters or you're given liters, you got to make sure you're at STP, because only at STP that 22.4 liter per mole relationship is true. Okay. And this flow chart right here puts it all together. Use this flow chart to help you through these calculations. Okay. Look at the reaction that you're given. Look at the flow chart. Mark where you're starting and where you need to go. And this will give you the steps to get there. Doing these for a bit will make things a lot easier for you to grasp. Okay. All right. That being said, congratulations. Chapter 13 done. We're down to 2 chapters to go. And let me tell you, they're short chapters. We're getting close. All right. Somebody had a question. I don't understand. Oh, there it is. Single replacement. You are correct. I didn't see that. What I want to do is just very briefly share with you this is the worksheet that's on the web site. This is the worksheet for chapter 13. If you haven't downloaded it, do so. This really has some more additional problems for you to work with, so you can get a better grasp of the topic, this particular chapter. And this is true for all the worksheets. Okay. And I just want to briefly go over this one here. This is an interesting reaction. It's very, people know that taking sugars, complex sugars like glucose is a combination of 2 sugars. No, excuse me. Let me change that. Anyway, this reaction is the fermentation of glucose. Okay. Not 100%, because some of these sugars that are broken down, they're more complex, and one of them is glucose, and this is what I meant to say. Glucose, the general formula for glucose is given there. It has 6 carbons. Let me zoom it up a little bit. Okay. It has 6 carbons, 12 hydrogens, and 6 oxygens. They're really alcohols, actually. Sugars are polyalcohols that have the OH group, which we normally think of as the hydroxide when it's ionic. When it comes to organic compounds, which again are covalent, they're not going to break apart. Covalent compounds that have what's called an OH group are classified as alcohols. a lot of the carbohydrates that are out there have multi-OH groups or polyalcohols. Okay, and so glucose in itself is polyalcohol. Now, what happens is the reaction is given here. Glucose is then broken down through the fermentation process and creates what we know as ethanol. Okay. And that ethanol, here's the general formula for it, is C2H5OH. Now, we're not dealing with organic compound, but that's okay because the formula, the structure for this is, you can see it's, change the color a little bit here, is this, but that is written as follows. It's a carbon with 3 hydrogens bonded together, bonded to the central carbon, and there's that other carbon is bonded to a second carbon. And that second carbon also has 2 hydrogens bonded, but then you have the OH. This is what makes the OH in covalent compounds makes it an alcohol, okay? Not a hydroxide. It's called a hydroxide group, but it won't dissociate like ionic compounds. So this is what you're familiar with as far as drinking alcohol. Now, you're also familiar with another alcohol. This is called methanol. Okay, methanol is just simply 1 carbon with 1 OH. Ethanol is 2 carbon. And I know you're familiar with propanol, or you might see it named or hear it named as isopropyl alcohol. And that is 3 carbons with the alcohol group in the central atom. Central carbon, I should say. Okay, that is the rubbing alcohol. But there's 2 types of propanol. That's that one. And then the other type has the alcohol on the end of one of the carbons. So this is 2 propanol, and this is 1 propanol. I know that's a lot of information here, but I just wanted to give you a side note about alcohols. And you got to be careful when it comes to alcohol because the methanol, if you ferment your own alcohol and it's not done properly, you can create not what you want, the ethanol, which is, I don't want to say the good alcohol, but the one that won't cause blindness. Methanol in high quantity can cause blindness. So if you have, you got your own factory at home generating alcohol, make sure you're not creating methanol, which can cause blindness. Now, with that being said, probably got too much information there. That's okay. You also generate carbon dioxide. So if you're making beer at home or you're making wines and it's bubbling, that's what's happening. It's bubbling because of carbon dioxide being created. All right. This is a generation-old process. Alcohol has been made for years. Okay, so you take in glucose, create ethanol, and carbon dioxide. Now they're asking you here is calculate the mass of ethanol if 500 grams of glucose reacted completely. And so you have 500 grams of glucose, okay? How many grams of ethanol, alcohol, do you create? All right, well, the first thing we need is the molar mass. And when I see reactions like this, I know when I see, questions like this, I realize I'm going to be asked for the molar mass. And so I calculate the molar mass for everybody right out the bat, just in case if I need it. So this one, I get 180.18 grams per mole for the glucose. Ethanol has 46, take my math here, 0.08 grams per mole. And carbon dioxide has 44.01 grams per mole. So I went ahead and just did all of them just in case there's other questions that I need. That's a 44, sorry. So that's what I come up with as the molar mass for all the reactants. Now, I'm only concerned right here between ethanol and glucose, okay? And so the question is, calculate the mass of ethanol produced if I start off with 500 grams of glucose. Well, like we've been doing, it doesn't make a difference what type of reaction you're dealing with. It's the same process, okay? We got all the information we need here. We got a balanced chemical equation. You didn't have to balance it, okay, because it was balanced for you. Yeah, I was checking it. Didn't look balanced for a second, but it is. I got 6 carbons in the form of glucose. I got 4 in the form of ethanol and 2 in the form of carbon dioxide. Carbons are balanced. Hydrogens, I got 12 in glucose. Well, you're going to work this through. I got 6 in ethanol. 5 of them are in the structure. You got the one of them out there with the oxygen. So it's a total of 6 for each one. Each ethanol, there's 2 of them, so there's 12 hydrogens. We're good on the hydrogens. And then the oxygens, we got 6 in glucose. We got 2 in the form of ethanol and 4 in the form of carbon dioxide. So we're good on that. So everybody's happy and everything's balanced, so we're good. I just need to double check sometimes. There could have been a typo, but it's not in this case. So calculate the mass of ethanol. Okay, 500 grams. So you write down what we got. 500 grams of glucose. Okay. Well, we know that we need to get to moles, and we divide by the molar mass. 180.18 grams of glucose gives us moles of glucose. I'm just going to call it G, okay, for glucose. Okay. All right. So that gives us 2 moles of glucose because our grams of glucose cancel out. We got that right. All right. So now we need to get to moles of ethanol. And we know from the balanced chemical equation, this is shorthand for ethanol, ETOH. Okay. And 1 G glucose. I'm just using shorthand. I want you to make note of that. G is glucose. So I got that canceled out. Okay. So now I'm at the moles of glucose. Excuse me, moles of ethanol. So I went from grams of glucose. The first factor gives me moles of glucose. The second factor now puts me into moles of ethanol. And I need to know the mass. So finally, I need the atomic weight or the mass, molar mass of ethanol. Okay, so which is 44.01 grams for ETO, moles for ETO. Okay. So I got that set up, and that should, number-wise, I think I got it here, at 255.7 grams of ethanol. That's a lot of ethanol there, guys. So that's number 1 grade moonshine. So anyway, you would have to distill it, get it out of there, because what's left is could be about a lot of junk. and stuff. Anyway, unless you use um, straight glucose, you know, there's a lot of times the sugars, like I said, are complex, and you take an enzyme to break it up. But if you take the straight glucose and again ferment to, then you got the ethanol. But then you still got to boil it because you still got a pot of junk that you got to remove. So anyway, that's what you have there. All right, so I'm not going to go through the other ones, but I just wanted to refresh your memory about the worksheets, okay? Because the worksheets have a lot of examples that you can continue to do. Here you got the one, the next one's calculate the volume of carbon dioxide produced at 0 degrees STP. Which would be kind of, you think about it, I don't know why you want to do you want to do this reaction at 0 degrees. It would take a little bit longer, you know, simply because of the low temperature. But anyway, they're asking you calculate the volume of carbon dioxide produced at STP if you started off with 100 grams of glucose, okay? And then the C part, they're telling you, okay, I created 17.5 moles in ethanol. How many moles of glucose were there to begin with? So you're working from product to reactant. And you got more examples. Okay, so by all means, here's a question number 2, zinc metal hydrochloric acid. That's another example of a double replacement reaction. Okay. You'll find that zinc is a lot more reactive than hydrogen, and therefore that reaction will proceed. You'll make zinc chloride and hydrogen gas. Okay. Number 3, my suggestion for number 3, that you're given the names. Okay, here you go. If you dissolve lead to nitrate and potassium iodide in water, they react to form lead to iodide and potassium nitrate. You know, put everybody into ionic form before you write the reaction, and then write the direction. Put everybody in ionic form so you can write the formula correctly, and then to balance it, follow the polyatomic ions. Okay, and then answer the questions, balance it like you've done to balance it, and then the questions are just like we've been doing before. Okay, here's a number 4. Oh. Right, then balance the combustion reaction of propane gas. Okay, propane gas, you remember, this is a combustion reaction. So one, you need oxygen, right? And remember when we talked about this reaction, the only 2 products you get are carbon dioxide and water. Okay, so oxygen, here's the formula for propane gas. Then you got carbon dioxide and water as the products, and then oxygen is the other reactant. And let me go through that one real quick to help you remember here. So we got propane gas, which is C3H8 plus O2. It's combustion reaction. The only 2 products are you going to get is carbon dioxide and water, carbon dioxide and water. All right, and since we're burning this thing, everything is a gas. Propane is a gas, oxygen is a gas, water vapor, and carbon dioxide is a gas. Okay, now recall how we balance this. Number 1, you do the carbons first. So we got 3 carbons on the left side, we need 3 with carbon dioxide. Number 2, balance the hydrogens. We got 8 hydrogens on the left side, we got 2 on the right side, reactant side, so we put 4 to balance the hydrogen. So we got 8 and 8. And then finally, number 3, balance the oxygens. Okay. On the product side, we got 4 in the form of water and 6 in the form of carbon dioxide. So it's a total of 10 as products. So we need to balance it on the reactant side, so we got a 5 sitting there. Okay. So there you go. You're set up. Now you can answer the questions. Okay. And the first question is, if 5 grams of propane are burned completely, what is the volume of carbon dioxide? So in this case, we're talking about carbon dioxide and propane. And if it's 5 grams of propane, how many liters of carbon dioxide are created is the question. All right. Let me see here. All right, and obviously we give you the key there, but don't look at the key. Okay, don't look at the key until you attack the problems and you're able to come up with all the answers. Okay, and when you're confident that you set it up properly and you got it right, then take a look at the key. And if you're incorrect and you don't see why you're incorrect, by all means, bring it in on Tuesday and we'll go over it. Okay. All right, so we'll let it stop there.